All right. Let me begin with a word of prayer. Dear Father, we thank you for this time to meet and study your creation. We thank you for differential equations, and we can understand about them. Help us to glorify you in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So, there's your favorite code on the board. Let's see here. Not really. The attendance sheet's going around. So there's also that. Now, so last time we started going over the theory of the nth order differential equation, and we'll wrap it up here. It won't take us long. If I can turn off the... Oh, wait a minute. I just remembered. This room is low tech. Wait a minute now. This way. There we go. So last time I shared with you the existence and uniqueness theorem that given any nth order differential equation, if the coefficient functions are constant, then there exists a solution to the initial value problem. All right. And so if we have such a problem, all right, L of y equals to f, and we have a set of solutions, y1 through yn, and they're solutions not to the whole differential equation, but rather to the corresponding homogeneous equation. All right, if that's the case, if those n solutions are linearly independent in the sense that we defined last time, you know, in terms of you can calculate the Wronskian. Whoa, bless you. Again, this theory is nothing to sneeze at. And so then this is linearly independent solutions to not the problem, but the corresponding homogeneous problem. If you have that, they're said to be a fundamental solution set. So for example, if you have y prime prime plus y equals to f, f could be any function, right? But in this case, cosine x and sine x form a fundamental solution set. Because why? Because the Wronskian of cosine and sine gives you 1, so they're linearly independent. And it's second order, so that counts as a fundamental solution set. But notice that sine and cosine don't solve the given differential equation, they solve the corresponding homogeneous differential equation, right? Because second derivative of sine or cosine plus itself doesn't give you f, it gives you 0. All right? So this is a fundamental solution set. All right, so the next big theorem is that there exists a fundamental solution set for any nth order problem. And the solution rests on the theorem I shared with you guys last time, namely that if we have an nth order problem with continuous coefficients, we can solve a initial value problem. So in order to solve an initial value problem, we make up some initial values. The initial values I choose are the y1 of x1 is 1, y2 of x prime naught is 1, but everything else is 0. So basically I'm assuming the initial conditions that I have 1 for the function, 1 for the derivative, 1 for the second derivative, all the way out to 1 for the n minus 1th derivative for the function. And I know this function exists because of the theorem we talked about last time. And so when I put that all together, my Wronskian at the point x naught is simply the determinant of the identity matrix, but the determinant of the identity matrix is 1. So that's of course non-zero, right? And because we have Abel's formula we talked about last time, that gives us linear independence of the solution set. And as such, since this is an arbitrary problem, we've just showed that every nth order linear differential equation with continuous coefficients in fact has a fundamental solution set. But there's more than that. If you have a fundamental solution set, then any solution you form for the problem, right? Any solution I form for the problem, the homogeneous problem, L of y equals to 0, any solution to that can be written as a linear combination of the fundamental solution set. So I can write the general solution for the homogeneous problem as c1y1 plus c2y2 plus da 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 plus cn. Now this is somewhat familiar to you guys because we did systems already, right? But understand that these aren't vectors of functions anymore. We're just talking about a scalar solution to a scalar problem. It's just nth order as opposed to saying n separate differential equations like we did before. The good news is we don't need eigenvectors here, all right? It's just algebra. The proof rests on the previous theorem. So because we have a fundamental solution set from the previous theorem, we just need to find constants C1 through Cn, which, you know, write y like that. So if I differentiate, so here's my first solution. As I'm trying to find the constants, do the constants have the claim is that there's a unique set of constants that does this, and so here's y of x naught, y prime of x naught, y n minus n of x naught, right? And that by differentiating and n minus 1 times differentiating gives me this stack of equations, which if I rewrite it like this, I get this. But then the thing is, this matrix right here is the Wronskian, right? It's the Wronskian of those n functions, which we know is an invertible thing. So we can solve for the constants and get a unique solution to the initial value problem here. So any initial value problem, we can choose specific choices, unique choices, in fact, of C1 through Cn, which reproduce this set of outcomes using y1 through yn as our basic building blocks, is basically the point. And I know I can do that for any choice of initial conditions because that matrix is invertible by assumption of the linear independence of the functions. Excuse me. And then finally, my last bit of theory for today, and then I'm going to put this, theory I'm going to project for today at least. I'm sure that we'll need more theory. We need, theory builds the machine to calculate in here. But the last bit I'm going to project here is if we have an nth order linear differential equation with continuous coefficient functions on an interval I, and we got the fundamental solution set y1 through yn, any solution of the non-homogeneous problem can be expressed as a linear combination of the fundamental solution set, these guys, plus something else which we call a particular solution. Now the particular solution actually is an honest-to-goodness solution to the given non-homogeneous problem. And this is then the general solution to the particular, to the non-homogeneous problem. The proof of this is actually pretty, so the previous ones, you know, if I was to give the proof of those on a test, it would be like kind of like a bonus question or something. Like I would just be curious to see if the math majors actually paid attention, that kind of thing. But this is something everybody could solve. So suppose you have, first of all, we have another theorem which tells us that there are solutions to this, all right? And there's one for each set of initial conditions. Well, okay, so suppose you had two different solutions for y, L of y equals to f, not necessarily with the same initial conditions, right? Well, if you look at their difference, you get what? Since L is a linear operator, you get L of y minus L of p. But these are both equal to f by assumption. F minus f is 0. What's that mean? That means that the difference between your two solutions is actually equal to a homogeneous solution. But since this is a homogeneous solution, it can be expressed as a linear combination of the homogeneous solutions, YH. We just call it YH. So in other words, but YH has, by the previous theorem, is a linear combination of the homogeneous, the fundamental solution set. And so in general, your solution has the form particular solution plus homogeneous solution. Please notice that the particular solution here does not have constants like C1 through Cn in it. The way I think of it is this, guys. The constants C1 through Cn forming the homogeneous solution, as we've seen in the derivation of this, they refer to the possibility that we can solve the differential equation with respect to different initial conditions. So because there's an infinity of possible different initial conditions, you need constants to reflect that variability in the problem. But the particular solution is not like that. There's just one forcing function here, f, that you're trying to output. And so there should be a unique solution to the particular solution. There's just one for a given f, and we'll see that. All right, so that's it. That's the backdrop. This is what we're up against. Let me put the projector away, and let's look at, let me just state the problem we're facing and what we're up against here. You guys have a good weekend? Well, you're all here, I guess. So you didn't get like washed away or something. That's good. My mom, I was going to try to tell my mom that she lives in Banner Elk, North Carolina, which is in like the high country, you know, of North Carolina, nearly Tennessee. And well, last time I talked to her, they had 10 inches of rain. And then I've been looking at pictures of the county where she lives, and it's messed up. Like, it's bad. But so let's see here. Summary. So I was going to offer her to come here and stay with us for a few days, but I've been told by my other various relatives that she can't leave because the roads are broken. Like, literally, she can't leave. So that's kind of a strange situation, but excuse me. All right, so to solve L of y equals to f, where, remember, L is equal to an d to the n, and I'm changing the notation now, guys, because it's driving me nuts. An minus 1 d to the n minus 1, a1d plus a0, and an, a1, a naught, f are continuous on I, which is the domain of definition. We need to find, number one, a fundamental solution set. y1, y2, yn, which are linearly independent, and we also need the L of yi. I'll do say L of yj is equal to 0 for all j. And then number two, we need to find the particular solution, yp. And number three, y equals to c1y1 plus cnyn plus yp. This will be, the solution to our given problem. That's it. This is your life for the next about 2.5 weeks or so. That's what we're up against. That's what we're trying to do. Figure out how to find these fundamental solutions, and then once we've got that settled, we'll circle back and figure out how to find the particular solution. But first up, we must solve and find the fundamental solutions. All right. So in times past, I have still continued into this story arc of the course with another about 2 hours of theory. But I find that when I do this, you guys get weary after about the 3rd hour of theory for some reason. So, I mean, that would be the most logically efficient path. But instead of taking that path, I'm going to take a little bit of time just to show you the method without too much theoretical justification. And then what we're going to do, once we've had a taste of how to find the fundamental solutions, all right, then we'll circle back to the theory and complete our logical due diligence, okay? And that's not just for the sake of being logically complete. It also motivates what's called the annihilator method, which we'll want to learn. All right, so lemma. If your linear differential operator is equal to P of D, where P is a polynomial that is, so let me write out what I mean by that. So like P of D is something like an d to the n plus an minus 1 d to the n minus 1 plus dot 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 plus a2d squared plus a1d plus a naught. So it's literally where what makes this polynomial is that the an all the way out to a naught, these are just constants, like real. I mean, this would still be true for complex constants, but let's keep it real for the time being, okay? You guys with me? Well, I hope you're with me. Give you a second to catch up here. So this is just the setup, the backdrop, all right? If this is all the case, then L of y, well, let me say it this way. Then L of e, okay, student choice. Do you guys want to let d be d dx or d dt? Your choice. T? All right, t it is. So we have e to the lambda t.
Actually,
X? I don't know. What?
no, better
That's too late. I only. Now you're stuck with x. Don't worry, I'll test on both. So L of e to the lambda x is equal to P of lambda e to the lambda x. That's the lemma. Let's see why that's true. So if we take L of e to the lambda x here, we've got, an nth derivative acting on e to the lambda x plus dot 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 dot. I'll go all the way down here to a2d squared on e to the lambda x plus a1d on e to the lambda x plus a0. I'm almost running out of space here. What am I saying? I've got plenty of space. Plus a0. There we go. So I'll do one of these. So what happens when you differentiate e to the lambda x? Well, you get lambda d to the n minus 1 e to lambda x, right? Lambda a2 d e to lambda x plus lambda a1 e to lambda x, and then plus a0 e to lambda x. I just did one of the differentiations, right? The key thing here, guys, is that if I take the derivative with respect to x of e to lambda x, what do I get? I get lambda e to lambda x, right? That's the fundamental truth of calculus here that binds us.
Why is there no lambda in
Because there's no differentiation there. Yeah. So, and then this continues, beep bop boop bop, and eventually we get n-fold differentiations for the first one, which gives me lambda n times a to the n, and e to lambda x, and then dot 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 dot. I get two of them down here, and I get one of them from this one. I get none of them, like you're just asking me about down here. At this point, we're like, e to lambda x is everywhere. Let's factor it out. So here we go. We've got an lambda to the n, a2 lambda squared, a1 lambda plus a0, all times e to the lambda x. But what did I mean by P of D. And what did I mean by P of lambda anyway, guys? I just stated it like you'd understand it, but did you understand it? What do we mean by P of D versus P of lambda? These are very, very different things. See? P of D is an operator. Right? P of D is an operator. P of lambda is a scalar. It's just what you get from plugging lambda into the polynomial P. Right? So that's the funny thing about polynomials. You could make an operator out of it, you could make a scalar out of it, depending what you want to do. Yeah.
So is this lambda the same thing as like lambda in the eigenvector?
Lambda is just a notation for a scalar we don't know. So no.
But it's not the same relation.
It's not the same. Well, this is a different problem. But in as much as you can make one problem into the other, yes, it's exactly the same lambda. There's a way to make that precise, but conceptually at the moment, no, it's not the same. But if I was to, for example, take the second order system and, well, we're not there yet. I can't answer your question yet, unfortunately. So yes, but no. But that is why I use the same letter. And the book uses R because the book thinks R is less confusing. But of course, I'm interested in confusing the students, so I insist on using lambda. Because my goal is to confuse the students, of course. That's part of my larger program of pedagogical, my adversarial pedagogy. That is a joke, just to be clear. But anyway, so this is P of lambda. That is literally P of lambda right there. So what good does this do us? We'll check it out, right? So theorem, P of D on y equals to 0 has solution given by y equals to e to the lambda x, where P of lambda has to be equal to 0. I'm not making any claims about the generality of the solution yet. I'm just saying we can find solutions, all right? So let me just like go through that. So because we know P of polynomial in D acting on e to the lambda x is equal to what? It's equal to P of lambda e to the lambda x by the lemma, right? So if we look at, you know, if P of lambda equals to 0, what do we got? Then P of D acting on e to the lambda x. And let me put some brackets in here just for good measure, guys. I do try to put brackets for operators, so let me not be lazy and leave the brackets off. The brackets serve us well. Let us put the brackets in. So this P of D is an operator. It's eating the function y and giving us 0. All right, so this operator P of D is eating the function e to lambda x, and it's giving me that as an output. This is an operator. It's eating this, and it's giving me 0. Which is to say that y equals e to the lambda x is a solution to my differential equation, P of D times y equal to 0. Okay, let's solve some problems. Example 1. Suppose I have y prime prime minus 3y prime plus 2y equals to 0. Right? In other words, this is d squared minus 3d plus 2. That operator acts on y and gives me 0. Right? So this is my quote-unquote, you know, my P of, you could say P of lambda is lambda squared minus 3 lambda plus 2, right? Agree? All right, factor it. So we've got lambda minus 1, lambda minus 2, right? Now why would I factor it? I'm going to say where that equals to 0, it gives me either lambda 1 equals to 1 or lambda 2 equals to 2. So what's that all tell me? That tells me that I have e to the x and e to the 2x. Let me call that y1 and y2. These are solutions. Hey, but this is a second order problem, right? This is a second order problem, so the theory we just went through tells us that I can write down the general solution now that I have these two. Is it clear those are linearly independent? Well, I'll tell you, it is. It is clear that they're linearly independent. You can calculate the Wronskian of them. We'll prove it in general in a future lecture, but for the moment, just trust me, they're linearly independent. Y equals c1 e to the x plus c2 e to the 2x. There you go. That's your general solution to this second order problem. Done. Not so much as an integration or an eigenvector in sight. But what is there? Algebra. Right? You must factor carefully. If you do not factor carefully, you'll get these wrong. Wait a minute, let me recap what I just said. I said that if you can factor a quadratic equation, if you can solve the quadratic equation, you can write down the solutions to the second order problem. Goodness, that's simple, you know? Let's look at another one. Y prime prime plus 10y prime minus 23y equals to 0. If you don't mind, I'm going to skip the operator step and go straight to the equation in lambda, right? Because that's really the issue. So we're trying to solve lambda squared plus 10 lambda minus 23 equals to 0. See, because we know that any solution to that equation, by the way, this equation has a name. It's called the characteristic equation, just like we called it before. So your conspiracy of it being the same lambda looks like it's starting to get more true. Guilt by association, right? Same name, also so-called characteristic equation. So solutions to the characteristic equation, because of the theory I just shared with you, this simple bit lemma and the simple proof, will give us solutions to that problem. So how do you factor that? Quadratic equation is wrong. I think I'm going to make that illegal in here. And the reason for that is everybody who used the quadratic equation on the last test did it wrong pretty much. So quadratic equation is not your friend. It does not help you because you guys are not that careful with arithmetic, unfortunately. So like it seems like it's an answer, but what it is an invitation to make a mistake. And so there is a better way, which is called completing the square. Let me teach it to you. So what we're going to do is we're going to take half of the coefficient of the linear term, which is 5 in this case, right? So I do lambda plus 5. I square that. This is the completing the square step, actually, mostly that. But the way I understand it is this. To be fair, when you square out this business right here, right, you get these two terms, right? Because you get lambda squared plus 5 lambda plus 5 lambda, which is lambda squared plus 10 lambda. But what else do you get? When you FOIL that out, you get a 25, right? Is there a 25 to start with? Well, there's not. So to be fair, I subtract 25. So with that adjustment, this and that are identically equal. Right? That is it. That is completing the square. That's all there is to it. And you can do this wherever you find it, whether the polynomial is in the numerator. If it's a rational function and this is something in the denominator, you can still complete the square there. We're going to need to do that later in this course because we're going to do something called Laplace transforms. There we won't have an option. There's no equation. We're just manipulating an expression, so we need to do it down in the denominator, for instance. This is something you should learn if you don't know it already. Now, if you're like me, and I'm not joking, like I literally did not learn completing the square until this course as an undergraduate. It finally hit me one day. Oh, that's completing the square. That thing I'm doing with the quadratic equation is unnecessary and slow. Why am I doing this? Just to spite my algebra teacher because I didn't want to learn completing the square because it's too complicated. Well, it was too complicated the way she was teaching it for me, but you can learn it. If this way doesn't delight you, find a tutor who can say it in a way which is less, I don't know, objectionable. So we've got lambda 5 plus lambda plus 5 squared minus what? 48. All right. And then what? Well, then this factors as follows. Lambda plus 5 plus the square root of 48. Oops. 48. Lambda plus 5 minus the square root of 48. What am I doing there? I'm doing the difference of squares formula, right? So mission critical to algebra is this. You must be looking for this. A squared minus b squared is a plus b times a minus b. That is of critical importance here. All right. And okay, so once I've got that, then you can see, okay, so lambda is equal to minus 5 plus or minus the square root of 48. Yeah? And as such, my solution looks like y equals to c1 e to the minus 5 plus the square root of 48. I'll throw you guys a bone. T plus c2 e to the minus 5 minus the square root of 48 times t. Now why do I put the t there? If I put the t there, what does that mean about the problem? See, this is prime notation, right? It's ambiguous. You could go either way here, couldn't you? But I'll say where, in retrospect, y prime is dy dt, right? So that makes t the independent variable, and as such, our solution should be written in terms of the independent variable. And there it is. That's the general solution right here. Yep, yep. Now, of course, you could simplify square root of 48 to whatever that is, 4 root 3. I don't care. All right. Any questions? Would it be helpful if we just took 10 minutes and just did factoring polynomials for a minute? Yeah.
It might be a stupid question.
Uh-huh.
But, are there any instances where this is not the best solution for the quadratic formula would be better?
It is, as far as I know, always the case that completing the square is better than the quadratic formula for manipulating equations. Now, do there exist like applied problems that have like microfarads or stuff like that in them where I would rather use the quadratic formula? Sure. But in terms of like symbolic manipulation, differential equations, completing squares is unassailable. Yeah. Yeah. Oh yes. So let's if you guys don't mind, I'm going to shift away from lambda and use x for I'm going to use x for polynomials for a couple minutes here because I think it's probably for your best if I do that. So let's just take 15 minutes and talk about how to factor, right? We'll come back to how to solve differential equations. This already gives you a window. As long as so if we have a second order problem, right? As long as we have as long as we look at the characteristic equation, it's got distinct real roots, we just write down the solution like example 1 and 2, right? That does beg the question, what if there's a repeated root? What if the root's complex? How does that go, right? You might already guess about the complex case based on what we've already done in this course, but we'll come back and we'll derive those carefully another day. The remaining time I'm going to devote just to talk about how we factor polynomials. So let's get into it. And because you guys are more comfortable with x than lambda, let's do a bunch of work in x. I guess I'll start right here. So let me get on my soapbox for a second here. I don't understand why we don't teach completing the square as primary. Like, to me, the other method that you're taught, guessing and checking, is an inferior method because it involves guessing. So like, example 3. You see what I mean? So like, x squared plus 5x plus 6. Now, admittedly, this is easier with just guessing, right? You should all be able to immediately write down what? X plus what? Right? Oh, wait a minute. Oops. No, that's not true. What do we got? 2 and 3, right? So you got to guess. Cool. Here's how this goes with completing the square. And I'm not suggesting that this is a good problem to do, completing the square, and I just want to show you can. So I take half of 5, which is 5 halves. I square it. I subtract 5 squared, 5 over 2 squared, which is 25 over 4. Right? I have to add 6 to that. Well, 6 is what? 6 is 24 over 4, right? Make common fractions when you can. So now I can add them. I get, oh man. I was naively hoping I was past the cough this morning, but apparently it's just a matter of me talking more. Minus 1/4. But what is 1/4? So you see what this is. This is x plus 5 over 2 plus 1/2, x plus 5 over 2 minus 1/2. So here I'm saying that 1/4 is the square root of 1/4 squared. And I'm using the completing the square. I'm using the difference of squares formula again. See, it's a squared minus b squared, right? And of course, this is what? X plus 3, x plus 2. What is the difference between what I have up here and what I have down here? You're like, well, what's at the top of the board I understand, and it's a happy place for me. What I've done underneath is an uncomfortable new weird thing, right, for some of you. But I'd also like to point out it's mechanical, and we derived it. There's no guessing down here. I simply added, divided the middle term by 2, and I did the completing the square. I hope I did the completing the square. And then difference of squares and factored. There's actually no guessing here. So completing the square is mechanical. It just requires arithmetic. Another example. This one we won't be able to factor. X squared plus 8x plus, I don't know, 17. So we have x plus 4. We square that, right? I have to subtract 16. I still got the 17. Do you see what I did? I hope you see what I did. I took half of the 8, which gave me 4, and these two terms are literally equal to those two. That's all I'm doing. I'm changing the form of the expression, grouping all of the variability into a square. This is completing the square. Now this one's not like the others. This one doesn't belong. You know, this one has the following form, right? Notice the difference in pattern here. Now we have a square plus a constant. This is not the difference of squares. What does that mean? Can you factor this with real numbers? Right. Only with we need complex numbers to crack this nut. So what you do is you introduce I. How do I rewrite 1 as a square. Well, remember I squared is what? -1. So really this is x plus 4 quantity squared minus I squared. Now it's the difference of squares, and I can factor it. Not a quadratic equation in sight. I mean quadratic formula in sight, right? Factored. But what this does mean is that it's not the same example type as my examples 1 and 2, right? What do you think is going to happen in this case? If I was to, since we're here, and since we're doing it, let me get the most out of this example. Just comment, right? If we had y prime prime plus 8y prime plus 17y equals to 0, that means we get y equals to, e to the 4 plus or minus I. We'll say minus 4 plus I times x as a solution. So that would be a complex solution here. And how does that work out? E to the minus 4x, e to the ix, which is what? E to the minus 4x cosine x plus I, e to the minus 4x sine of x.
Constant multiplied.
At this moment, I'm not to the constants yet. So identify from this one complex solution, we get a y1 here and a y2 here, which we keep real. And so the general solution of that problem would be y equals to c1 e to the minus 4x cosine x plus c2 e to the minus 4x sine x. And there's your constants. And there's your general solution to this complex root characteristic equation. I'm sorry, I'm getting off track. I was trying to focus on algebra here, but I can't help but solve a differential equation. It's just there. Because that's the thing, is like doing the algebra is most of the work. So it feels wrong to not get something out of my algebra. But I'm going to focus here on more algebra. Oh man, example 5. Suppose I had x cubed plus 6x squared plus 9x. How would I factor that? Now this is a cubic, right? This is a cubic. This is something new. So what do we do? First opening move, factor out the x, right? Like so. And then what happens when I complete the square here? X plus 3 quantity squared, right? I have to subtract 9 then. Now I'm not saying you have to complete the square on everything, guys. I just want it to be a tool in your toolbox that you're willing to use. All right? I'm not actually going to stop you from using the quadratic formula, but it pains me to see you use it, especially to use it and get it wrong.
You don't need to subtract the 9. You can probably just factor x.
Well, that's my point, is that completing the square does that for you. See, I mean, I don't disagree with you, but what I'm telling you is, like, philosophically, I don't have to think through it. It's done for me by the machine of completing the square. If you understand this, you don't have to think anymore. So x squared plus 7x plus 1 factor x plus 7 over 2 squared minus 49 over 4. I'll change the 1 to fourths because we're going to add them. So that's, oh man, a 48 again. What the what? Well, that's funny. Did I do this problem already? No, we just had a 48 randomly in the other problem. So, there it is.
Should be a 45.
45?
Yeah.
Oh, good. Thank you. I want some diversity in my examples. There we go. That's better. Square root of 45. factored, right? Now keep in mind, if I'm looking at this equal to 0, this is also important. If this is equal to 0, what's my solutions? Minus 7 plus or minus the square root of 45 over 2, right? And you could see the quadratic formula here, right? But at no point did I look at the quadratic formula and plug numbers in, because that process of plugging numbers in and evaluating the square root, there is about a 40 or 50% chance students get that wrong on a test, in my experience. Something like that. I wish it weren't true, but it is. Now maybe there's a 40 or 50% chance you'll do this wrong too. I don't know, but like I want to be optimistic. I want to say no, you're going to get this right. Yeah.
And you said you didn't care if we like turned the square root of 45 into like 3 times the square root.
Oh yeah, I don't care about that. I mean, that will become important if you're trying to simplify an answer and match a book question or something like that. But short of that kind of chicanery, who cares? Example 7. Let us continue with this cavalcade of algebra. Let us suppose we have, I don't know, x to the 4th plus 10x squared plus 3. So here, I have to look at this as x squared squared plus 10x squared plus 3. So I complete the square in x squared. So I have x squared plus 5 squared minus 25 plus 3. Now here we're well outside the province of your quadratic equation. Your quadratic equation won't help you here unless you make an x squared substitution, which perhaps you would if you're, clever. But I guess this requires cleverness, however you slice it. But anyway, that's completing the square in x squared. And as such, we can make progress, I think. X squared plus 5 squared minus 22. All right. So that's x squared plus 5 plus the square root of 22. X squared plus 5 minus the square root of 22. And if you're wondering how that step goes, well, here's a way to see it. 22 is the square root of 22 squared, right? So you can see this as a squared minus b squared, with a and b having the meaning of x squared plus 5 and the square root of 22. That's how I look at it anyway. Now, what is the square root of 22? How does it relate to 5? Is it smaller than 5? Is it larger than 5? What's the deal? Smaller than 5, which means that this is positive. Well, that's obviously positive, right? But this is also positive, right? Because 5 beats it. What does that mean about this quartic? It's what? It's in the first quadrant. No. I mean, does this have any real solutions is my question. So the answer is no, right? Both of the quadratics that we're finding, they're irreducible. These are both prime quadratics. Both quadratic factors cannot be reduced over the reals. So if I was to solve the corresponding differential equation here, it would be a 4th order differential equation, and its solution would be in terms of sines and cosines, right? So I guess we got time for me to write that down. So if we were solving the 4th derivative of y plus 10 y prime prime plus 3y equals to 0, from this I can read off that I've got lambda is like minus 5. No, I don't have enough time to do that. My bad. The details will take me 3 minutes here, and I should let you guys go. So sorry. Anyway, I hope that is a helpful review of algebra. We'll be doing lots more algebra in here, but I think that's a good start. We also got to look at long division, because that matters.